All right. Is everybody ready to finish chapter 1, maybe start some chapter 2? Because I am. Okay. So has oh, yes, question. Sure. Get the internet so I can boot up. So it's going to be on facultyweb.berry.edu/aceaerobic. Chemistry lectures. So, sorry, this is 341. So 341 is all the links to like paper things. 341 lectures. So every day will be a new link. So if you want to go to the 26th. It'll load up that lecture.
Is there a link on Viking Web?
I don't use Viking Web because Viking Web won't let me post YouTube. So everything's on my, hey.
I need Dr. Davis's first OCAM.
Oh, next door.
Okay, thanks.
No problem. So everything's going to be on this facultyweb.berry.edu. And then 341 lectures. These are all the YouTube videos. So after this class, I'll post August 28th. And so if you know which day you're missing, you can just re-watch it. Is that good? Yeah. Any other questions about where to find my stuff? You need syllabus stuff, that's over here. You got syllabus, PowerPoints, the problem set, which we have our first problem set due on Friday. All these other things. I'm still working on the exam practice problems, but I should have those, I'm hoping by the middle of next week. Yes, ma'am.
I know we normally have quizzes on Monday, so we won't have one.
We will not have one this Friday. We'll definitely have one on Monday.
So not.
Typically Mondays,
Okay.
right. It'll be typically Mondays, and the occasional Friday group quiz, but I'll let you know in advance when those are going to happen. Questions?
So will we have one on Wednesday since we don't have class on Monday?
No.
Okay.
There's no quiz this week or Monday next week, because you have off. So there's a good chance I'll have one Friday of next week, and it'll be a group. Yeah, if I have them on Fridays, they're for group quizzes.
Will we know about the
Yes, always. Best I can, I will let you know the class period before. As long as I remember. It's always on my things to tell you. It doesn't always make it on the, I always remember to tell you. All right. Good on the website and all that whatnot? All right. All right, so let's finish chapter 1. All right, so we left off talking about the 4 main types of building blocks. We talked about our amino acids, our nucleotides, our lipids, our carbohydrates. So then the next section is talking about polymers. So organisms contain macromolecules, where macro just means a large agglomeration of molecules, that may consist of as many as thousands of individual atoms, which are built from smaller units. And these smaller units are only a few kinds of building blocks. But these few building blocks is like having a set of Legos that you maybe only have 20, 30 Legos, but you can build a bunch of different things from it. So that's kind of our building blocks. So they can be combined in many different ways. To produce a large variety of structures. So all four of those building blocks we talked about, the amino acids, the carbohydrates, the lipids, the nucleotides, can all be combined either with their similar ones, like you can combine many carbohydrates together to make a polymer of carbohydrates, or you can combine a carbohydrate and a lipid to make a new type of macromolecule. So those, we can either combine all of one or combine two different types, at least two different types. So we're going to talk about just three basic polymers that we're going to encounter a lot this semester, and what building blocks go into making those polymers. Oh, wait for everyone to catch up. I'll slide it up. So our first two major biological polymers, first one I'm going to talk about is proteins. All right, so what building block goes into a protein? Amino acids. I heard some whispering. Amino acids. Excellent. And how many, as I reviewed, how many common types of amino acids are you currently studying real hard? 20. Excellent. We'll talk about a few of the weird amino acids, but for now we're just going to do the 20 common types. So these 20 can be combined in any order for the most part. But amino acids fall into four categories typically, right? You got your hydrophilic, your hydrophobic, your charged, and your neutral ones. And so depending on what combination you have of those properties, the structure will change. So if you had a lot of polar ones, they're going to associate with the water. If you have a lot of hydrophobic ones, they'll want to associate with themselves rather than the water. So the way that they're combined determines their three-dimensional shape. And we will spend a lot of time talking about how the structure is determined by the amino acid combinations. So the way that we're going to combine those amino acids is going to determine their three-dimensional shape. Which means it's real important that we pick the right amino acids to do the right job. Okay, let's talk about nucleic acids. Nucleic acids, these are our friends DNA and RNA. So polymers for nucleic acids are going to be DNA and RNA. Does anyone know off the top of their head how many nucleotides are available? How many choices? Like we have 20 amino acids. Does anyone know how many? 5. I see it. 5. Yes. Which we will get to which 5 those are. But there are 5 possible nucleic acids. And so we have less options of how we can combine them together because we only have 5 possible things that we can combine together. So we have less possible three-dimensional structures that are available. What in general is a job of your DNA? If you had to pick just one thing that's really important that DNA does. It can repair things. Codes for protein. Anything else that DNA does? I'll throw out RNA. Makes copies for all those things. How important then is your DNA to be a strong structure that is the same every time? Very important. So that is going to be an important job of our nucleic acids, is to form a regular structure that can carry your genetic information every time successfully. So in proteins, we're going to have lots of different options of 3D shapes we can make. DNA, RNA, we really only have maybe 3 or 4 different shapes we're going to possibly make. And part of that is we only have 5 nucleic acids to combine together, so there's a limit on how many shapes we can make. Good so far? Let's talk about the third type of protein, or third type of polymer. Our good friend, the polysaccharides. What building block, we've already used 2 out of our 4, what building block makes our polysaccharides? Carbs, our favorite food group, carbohydrates. So it is a polymer of carbohydrates. While there are lots of carbohydrate choices, there's only going to be a few that have the ability to polymerize. So there are many carbohydrates, but not all have the ability to polymerize. So you wouldn't want to use your polysaccharide to carry genetic information because it doesn't make a real great rigid 3D structure. But what are some things that we could use polysaccharides for? Does anyone know anything polysaccharide? Or any one example of polysaccharide? Energy storage, that has a great job for it. What is a polysaccharide that is only, well, not really, mostly found in plants? Cellulose. What is the job of cellulose, biology folks? What is the job of cellulose in a plant? Structure, right? Its main job is structure. How do I spell cellulose? It's pretty close. So it's not great for transmitting information, but depending on what polymer you make, it could be really fantastic for fuel or energy storage. If it's a different kind of polymer, we're going to use it for structural support. There's a few other types of polysaccharides we'll talk about that have similar jobs to that. But those are going to be the 2 main jobs our polysaccharides are going to do. What building block am I leaving out? Lipids. Lipids do not polymerize. So let's put that as a little star down here. They aggregate. Does anyone know the word aggregate? what would you say aggregation looks like? What's another word in more common lingo? Collection, grouping, they kind of like lump together. So they don't make like a nice straight line. They're going to be kind of a blob, which is good if you want it to be a cell, right? They're going to blob together and make kind of a circle, or we'll have micelles, which make like little spheres. So it's good for that, but they don't polymerize. They associate head to tail. All right. Let's then talk about a little review of Chem 108 and 109. Maybe a little bit of physics in here. Just a little bit. Did you guys talk about a little thermo? 3 laws of thermodynamics. So I think you would all agree that activities of organisms constantly demand energy, although you guys look like you're in a low energy state right now. Later on today, you will need to eat, and that eating provides energy for all of your metabolic functions. And so the study of energy is thermodynamics. So we're going to talk about the 3 laws and how they apply to biochemistry. All right, can anyone name any one of the 3 laws? There's a 4th one that I won't get to, but we'll talk about it because I think it's funny. All right, anyone can name any one of the 3 laws? Yes, that's number 1. Energy is conserved. Cannot be created nor destroyed. All right. 2 or 3.
Is it that it can be transferred?
That's number 4. That's our 4th one that we don't really talk about. It can be transferred. So if you have ice cubes in your water, the water gets colder and the ice cubes get warmer, and so that's a net transfer of energy. So that's number 4. The other 2 deal with entropy. So number 2 is that energy is dispersed within a system and chooses to be more disordered. I guess given a choice. Missing this in there. And the 3rd law is that the entropy of a crystal at 0 degrees Kelvin is 0. Which doesn't sound like it's very useful, but just wait. Super useful. We'll use it in just a second. Ooh, that's crazy looking. All right, so what we're going to do is take a stroll through these 3 laws and see how they apply to each other and then apply them to biochemistry. So let's take a closer look at this first law. The energy is conserved and cannot be created nor destroyed. Okay, we consider the universe, which is everything we know in the entire sphere of our knowledge. It consists of 2 parts. The system and the surroundings. That sound familiar from when you did those coffee cup calorimeter experiments? Good memories, right? Coffee cup calorimeters. And so if the universe is made up of 2 parts, our system and surroundings, we can say that the system has a certain amount of energy. We're going to call that big U. And the system undergoes change in either heat or work. So a system undergoes change in either heat, which we're going to call Q, or work, which is called W, which means our change in energy has to be due to heat and work. Now, I'm going to assume that everything we talk about in here takes place on Earth. And so since I'm going to make that huge assumption that everything in this class takes place on Earth, the Earth is at constant pressure. If we are at constant pressure, work is the change in volume at constant pressure. Does any of this look familiar at all? A little bit, some of it? Good, good. Okay, so plugging this in to this equation and doing some rearranging. All right, all I did is I plugged negative P delta V in for W, then moved it so that the Q is on one side by itself. That is also equal to our delta H. What's the name of delta H? Enthalpy. So the first law that tells us energy is conserved and cannot be created or destroyed also tells us that the change in heat is the enthalpy, and it depends on energy of the system and the change of volume that's going on in your thing, in your system. Have I described anything about spontaneity yet? No, we got those other two laws. Let's talk about law number 2 and 3 and talk about spontaneity, which you guys are lacking right now. All right, so our second law, again, is that entropy tends to increase. And spontaneous processes are characterized by conversion of order to disorder. That all energy, given the choice, would prefer to be disordered and spread out over a larger space or larger volume. So S is entropy. If I want to talk about the increase of entropy, does it have to be greater than 0 or less than 0 to become more disordered? Think about it for a second. We'll back up. Let's talk about H. This is a separate, we'll go down here. Okay, if I'm talking about spontaneity and enthalpy, does enthalpy need to be a positive number or a negative number to be more likely to exist, or more likely to happen, more spontaneous? Negative, all right, that's definitely less than 0. All right, entropy, does it want to be a negative value or a positive value to become more disordered? Positive. Okay, so we want our entropy to be a positive number, our enthalpy to be a negative number, and we're going to combine those things together and talk about our third law. So for a spontaneous process, we just said delta H has to be less than 0, delta S has to be greater than 0.
spontaneous process means the more disordered the system?
Yes. If it is likely to be spontaneous, it means that it is more disordered. Or that the enthalpy, the change in heat, is so great that it's making up for the lack of entropy. So combine these two things together. So it's most likely to be spontaneous if I have my delta H minus T delta S. That value is less than 0. And it's because we defined that. Where our Gibbs free energy, not to be confused with the NCIS guy, not the same guy. Apparently very few people watch that show. All right, Gibbs free energy is our delta G value, and it tells us about the spontaneity of our reaction. So if I have delta G less than 0, my reaction is likely to proceed. So I got the right kind of heat, I got the right kind of entropy, most likely go forward. That all sounds familiar? Vaguely recalling. Okay, no one's nodding, which means you guys are thinking really, really hard about it, so that's good. Questions about our 3 laws? So let's talk about why is life thermodynamically possible? So for life, or any organism to exist, it must have thermodynamically spontaneous reactions occurring within it. But if I took out just one cell by itself, its overall process, or even one step in the citric acid cycle, or one step in oxidative phosphorylation itself, may have a delta G greater than 0. If it's greater than 0, is it spontaneous or not spontaneous? Non-spontaneous. But your overall citric acid cycle definitely proceeds forward, even though there are steps within it that are not spontaneous. So how does your body overcome that issue? So let's take an example. Let's say I have this reaction, and then it goes on and does that reaction. This one has a Gibbs free energy of 20 kilojoules per mole. This one has a Gibbs free energy of minus 30 kilojoules per mole. Is this A to B spontaneous or not spontaneous, the way I've written it? Okay. Is this B going to C spontaneous or non-spontaneous as I've written it? Okay. This is spontaneous. Let's say I'm interested in the overall reaction of A going to C, going through this intermediate stage of B. So remember what I can do with my free energies to find a new total free energy? Add them together. So now my new reaction, A going to C through B, has a delta G of minus 10 kilojoules per mole. Spontaneous, not spontaneous? Spontaneous. So what we're going to see in things like oxidative phosphorylation and citric acid cycle and a few other things is that we're going to link reactions together so that maybe an individual reaction is non-spontaneous, but the one immediately following it is so spontaneous, it just pulls it right through that high transition energy. So cells, or cycles, are going to couple unfavorable metabolic processes with favorable ones You could change that to non-spontaneous and spontaneous. So that the overall reaction delta G will be less than 0. We'll talk about that a lot in the second half of the semester. We talk about individual glycolysis, citric acid cycle, all those. What's the delta G at each step, and how does your whole system combine those to make an overall spontaneous process? All right, this has all been about spontaneity. Is spontaneous the same thing as fast? No. Why is spontaneous not the same thing as fast? Does anyone have an example of a process that is spontaneous but not speedy? Iceberg melting, that's a good example. Like, it's more likely to melt because it's in water, and the water is definitely warmer than 0, but it sure takes a long time. I would say your life cycle, you guys are all likely to die. Hopefully not speedy. Hopefully you guys have another few decades in you, right? That is a process that is guaranteed to be spontaneous, but not likely to happen very speedy. So what topic talks about speed? Thermo is all about likelihood to happen. What's the other thing that we talk about in Gen Chem that talks about speed? It's on the next slide, if you are looking at the next slide. What's that big KEQ? Rate of the reaction. What does big K also talk about? It's another word that starts with K. Kinetics. So kinetics tells us about the speed of a reaction. So kinetics describes the speed of a reaction, which we can learn from our equilibrium equation. And we will spend a lot of time talking about kinetics, how fast a reaction is likely to go, why would you choose to have a slow reaction or a fast reaction, how does that tell you about the thermo. And they're related, right? You got your KEQ, and from A plus B goes to C plus D. I get this, where I got products over reactants raised their stoichiometric coefficient. So I have A, and B, C, C, D. All right, so I have A raised to the power of A and B raised to the power of B on the denominator. Sound vaguely familiar? Products over reactants. Yes, good. And that's related to delta G this way, where the power of E raised to the negative G divided by RT, and R is the gas constant, T is temperature in Kelvin. Good. So that'll be what your homework is on due for Friday. Just some review of talking about things like that. Any questions about chapter 1? In that case, let's talk about the best molecule on Earth. Any ideas what the best molecule on Earth is? Water. We're going to spend a whole chapter talking about water. So we're going to talk about it a little bit today, and then we'll finish it up on Friday. All kinds of great things about water, and why water is awesome. So, just as a fun fact, all biomolecules assume their three-dimensional shape due to the fact that they are in an aqueous environment. And by shape, I'm talking about three-dimensional shape. So let's do a quick review of like 2 or 3 terms. Let's see if I have it over here. I'll do the 2 or 3 terms in a minute when we get to them. All right, so all biomolecules assume their shape due to the fact that they are in an aqueous environment. So, aqueous environment. Let's talk a little bit about water and why water is such a unique molecule. So water is polar. And so I have here, I got my oxygen. In the center, I got my 2 H's, right? It's going to look like this. And if you're going to go back and do a VSEPR of it, right, each of these lone pairs get their own spot. So it's a tetrahedral shape, which is unusual considering that it's only 3 molecules. It's tetrahedral in shape. Because it's polar, what does polar mean when I'm talking about it just in general? Well, I'm saying it's a polar molecule. What's the difference between polar and nonpolar?
Charge.
Part of it's the charge. Unequal sharing of charge. All right, so if I was going to say which way are the electrons being pulled in this bond, are the electrons that hydrogen is donating? Is oxygen taking the electrons or is oxygen pushing away the electrons? It's going to take them. So I'll do that for both these guys. All right, the lone pairs. The lone pair is choosing to push their electrons back on the oxygen, or are they spreading out themselves into a gigantic oval shape, right? They're trying to push away both from the oxygen and from each other, which means overall, we have electrons being pulled in this way, but then the lone pairs are pushing out that way. And so it has a dipole moment, a constant dipole moment. Okay, what's another fun thing that water can do that very few other molecules can do? Because it contains an oxygen and a hydrogen. Like oxygen, nitrogen, hydrogen, and fluorine can do this fun thing. Hydrogen bond. It can not only hydrogen bond to itself, but to other molecules. And so because it can hydrogen bond to itself, it makes a nice crystal structure, right? That's why ice has a really solid shape that floats, and water is just cool, just in general. Yeah? Okay. Let's talk about all the different types of interactions that water can have with other molecules and other molecules can have with themselves, right? All right, so we have, these are all non-covalent, so that means they're transient, they don't exist at all times. So what does a molecule have to participate in an ionic bond? It has to have a charge. So it occurs between charged molecules. So water, in some of its forms, can participate in this. Right, those forms of water. Does anyone remember what snazzy word I use when I talk about OH minus? Okay, this guy's our hydroxide. And then this guy over here, hydroniums. So when water is in its either hydronium or hydroxide form, it can participate in ionic interactions. Okay, what does a molecule have to have? I already gave it away a few minutes ago. What does a molecule have to participate in a hydrogen bond? Has to have hydrogen. Hydrogen has to attach to what other three choices? Mm-hmm. So a hydrogen bond occurs between molecules that have a hydrogen covalently bound to a nitrogen or oxygen or fluorine. All right, these pictures over here are going to be for over here. So our dipole is this picture over here, the interaction between permanent dipoles. You have to have two molecules that both have a permanent dipole. So in this case, I'm showing just a C double bond O. It could be anything, I don't know, acetic acid would be a bad example. I'll just write down two molecules. Both the permanent dipoles. A dipole-induced dipole interaction means that you have one permanent dipole and another molecule that has just a real quick dipole moment. So in this case, I have that same C double bond O with its permanent dipoles interacting with a methyl group, which when they get close enough, the methyl group will kind of be pulled towards it and then float away. So they don't form a significant interaction. And then London dispersion forces. Any guesses what two kinds of molecules participate in London dispersion forces? We've done dipole-dipole, we've done dipole-induced dipole. Everyone's following my train of thought? Dipole-dipole, dipole-induced dipole, induced, or non-non, whatever you want to call it. So everybody can participate in a London dispersion force, for the most part. There'll be some part of the molecule that's non-polar and will interact with each other in passing. And then this is out of your textbook, just the table of bond energies. And bond energies is a way of telling you what is the strongest type of bond, right? Covalent will be the strongest, then ionic, then hydrogen, then dipole-dipole, then non-dipole-dipole, and dipole-induced dipole kind of falls right here in the middle between the two of them. All right, we will finish up chapter 2 on Friday. And on Friday, you will bring me your chapter 1 homework.